will start with thanking the organizer, right? And that gives me opportunity to not only to present results, but also to meet friends, colleagues, and to enjoy hospitality of Yerevan. So now I think I should begin with this. I talked about integration of valued functions OTHA event very recently. At that point, the results were not published and certain of the questions were open. So today my talk will focus on the first part mostly, integration of operator valued functions, but I will also mention something about integration of complex real measure valued functions. We are not going to integrate positive measures, but also real valued measures. Analysis changed at the beginning of the previous century, basically by getting a new integration theory and the beginnings of functional analysis, right? Hilbert spaces, Banach spaces, and later more general topological vector spaces, all kinds of things. Now, these two strands merged fairly early. There was a theory of integration for Banach space valued functions that developed in the 30s, and there are several names attached to this development. That is done for Yerevan and so on. And the influences went both ways. Measure theory influenced functional analysis, and functional analysis influenced measure theory. And then that was somehow summed up in this old and rather famous book by Distel and Wu, Vector Measures, 1970, almost half a century ago. And there is a more recent one, as you see now. Regarding integration of operator valued functions, that's an old topic if we are restricted to the case of the Riemann integral. Basically, one needs integration in problems related to the spectral theory, right? Resolvents and so on. That's an old topic. And then there is more recent development regarding integration of operator valued functions. That's the last, say, 25 years or so. You see, what we are doing is basically doing integration in Banach spaces, but in Banach spaces of very special kind. The space of bounded linear operators acting between two Banach spaces, and sometimes acting on a Hilbert space, right? And with values in the Banach space of complex measures defined on a sigma algebra of sets. Now, what about the motivation? Well, for operator valued functions, I told you already, some applications, though Riemann integral works just fine in such cases, but there are more recent research which was somehow specific to the Hilbert spaces and related to various ideals of compact operators, the Châtain classes being the most famous one of those. So there appears also integration of functions which take values in say certain Châtain class of nuclear operators or whatever. Now, on the second case, when we want to integrate functions which take values in the space of complex measures or real measures, well, I'm not an expert on this, but that happens in probability theory and also in some problems regarding variational problems. Well, calculus of variation. And now, a pioneering paper on integration of operator valued functions, which is different from the Riemann integral, is this paper by Yerevan, which I had plenty of troubles to find, but I did eventually, because that's 1936. Now let's start with the case of operator valued functions. So just to set up the notation, you have Banach spaces X and Y, and this H is reserved to stand for a Hilbert space, which is going to be separable unless stated otherwise, as they say. And then you have a sigma algebra M on a set omega and certain measure mu on that sigma algebra. And this C infinity does the class of compact operators X to Y. Now, because we are going to, at certain points, to deal with sequences of functions, because we want to prove convergence theorems like X-dominated convergence theorems or something of that sort, then it's convenient to denote functions. Okay, this is a family of operators, or a function which takes value in the space of operators. Now this is going to be a function which takes values in the Banach space Y. So we denote it by superscript, right? Now I already mentioned integration of Banach valued functions, Bochner, and Dunford integral. I might actually review it. Now, this is one thing, right? And now we are going to define Yerevan integral for operator valued functions and certain norm space. This PD stands for pointwise Dunford. It's certain type of a weak integral. And the one case appeared, as I say, in 1936 in a very specific context. So this is going to be more general. The Yerevan dealt with the Hilbert space operators. And then I might skip this because time is short. There is going to be a Banach space, certain Banach space you see, of operator valued measures, subspace consisting of, in certain sense, absolutely continuous families of operators. And then there's going to be embedding, this embedding, and this allows, there is a very natural norm on this space, and this embedding will provide a norm on this space by virtue of this embedding, just an induced norm. And then I probably will skip this one. There are natural operators acting on this space, right? One is basic integrate, right? And that you get integrate over a measurable subset, and you get an operator, right? And now there is going to be this point of development to get certain of the convergence theorems. There are others which we proved. This part, by the way, this first part is based on joint work with my PhD student, Mihailo Krstic. And he's also a PhD student of my colleague, so we are co-mentors. The other guy works in Hilbert space theory. Then there are some further results. Absolutely continuity property, weakly uniformly integrable families, and the Vitali convergence theorems. These are analogs of the classical scalar valued theorems, but there are certain assumptions and certain differences. Now, about the measurability, this is just a brief review. What is a simple function? Well, on a measurable set, it takes a constant value, a constant vector, otherwise it's equal to 0, and you know how to integrate such functions. And then you have a notion of strong measurability. If it's almost every limit of sequence of simple functions, which is simple function is a linear combinations of these functions which are determined by a vector in a space. This is C in Y, and a measurable subset of omega. All right. And then there is notion weak measurability, It's natural. You dualize, basically use duality and get a definition, which is a natural one. And now it's a big theorem, which I guess it's on this slide. Yes, it is on this slide. This is the famous Pettis measurability theorem. Strongly measurable equivalent to weakly measurable plus essentially separably valued. Right? You kick out a set of measure 0 and then the values form a separable subset of codomain. Now, Bochner integral, this is this L1 space. So it consists of strongly measurable functions with this standard classical condition, and we, as usual, make identifications, which I'm not going to talk about. And the point is, it is a Banach space, and then you can integrate over your space or even over a measurable subset, no problem. And the theory of Bochner integral is very much parallel to the theory of classical Lebesgue integral, so I'm not going to review this. You can prove convergence theorems. Of course, you cannot prove monotone convergence theorems because unless Zelina finds the order, unless you have an order on Y, you cannot get anything like this. Sorry, there is some comment. Yeah, the theory of Bochner integral is rather similar to the standard one, okay, and then you can prove dominating convergence theorem. Now, weakly integrable function is, okay, this is the definition. For any element in the dual space that you compose, you get a standard scalar valued integrable function. And then by using this, I'm going now hand waving, you get a bounded linear functional on the dual of y. So when you integrate, you get not, in general, not an element of y, but an element in the second dual as the value of your integration, right? And so this is the defining relation. So this belongs to the second dual. If it happens, if it just happens by coincidence or by reflexivity of y, that it's in the Banach space y, then you can of course exchange places of these two things to get to more usual notation. Okay, so if this is in the space itself, not in the second dual, then it's called Pettis integral. And of course, this is always the case if codomain y is reflexive. Okay, and now we turn to the point. Okay, we want to integrate operator valued functions, and you do it pointwise. You have a family of operators, A, T, right? Right? Pick a vector x in the first Banach space, in the Banach space x, and you get the family A, T, x. If it's weakly integrable, fine, we integrate it, and that's the value of the integral on the vector x. This is clearly linear, no problem. It takes a little bit of functional analysis, closed graph theorem and things like that, to prove that it's bounded, and it's indeed bounded. So this is the integral. Okay, basic theorems that this x to the second dual, and this is called pointwise Danforth or Gale-Funk or Beek or whatever integral of this family. And of course we can integrate to measurable subsets. So now you have two expressions. You want to put a norm on this space of weakly integrable functions. How to do this? One thing is, by definition, we fix x and y. This function as a function of t is integrable. So you take L1 norm of this. right? And then take supremum over all unit norms X in the Banach space X and all unit vectors in the dual space of Y. So this is basically based on the definition. Here, it's a bit different. So that's G in honor of Yerevan, for example. And this M means that it's obtained by using all measurable subsets of omega. You integrate over omega, get a bounded linear operator, fine. Take the norm of this and supremum over all measurable subsets of omega. Now, there are certain things to prove. A, these are norms. I mean, these expressions are finite. And if any of them is equal to 0, then that family is almost everywhere equal to 0, so you need to get that it's a norm. And to prove that it's that these two expressions give equivalent norms. So that's the theorem, one of the theorems. If the measure is discrete, mu, so take omega, the set of integers and the standard counting measures, for example, then this is going to be a Banach space. But in certain cases, this is not complete. And this is one thing that happens that it would be interesting to determine when is it complete, when it's not, but in some cases it's not. And the point is that this space of Pettis integral something is it works. The point is that the space of Pettis integral functions is not necessarily complete. There is a counterexample in this old paper by Liliana Janicka and Nigel Kelton, 1977. And now we have getting a little bit. Let's do some. Let's work in Hilbert spaces. And then you have a sequence of weakly measurable to begin with, functions with values in the space of operators on the Hilbert space, converges pointwise in the weak operator topology to a function A, right? And now you assume there is a certain function B which plays the role of integrable dominant, right? This is the meaning of this assumption. All these belong to this space of weakly integrable functions, and you can interchange limit and integral. And there are other theorems analogous for the strong and norm convergence. See, here is the assumption that you have pointwise convergence in the weak operator topology, and then this limit is also in the weak operator topology. If you replace weak operator topology by strong operator topology, you get the same result, and if you replace in a norm, then you get conclusion in a norm. Now, we all know the absolute continuity condition for real valued say functions on the real line or more general. This notion extends to families of functions defined on omega with values in this space of bounded linear operators, and this is natural definition. Now, the difference here is that a single integral family does not necessarily have this AC condition. And that's maybe a little bit surprising, but that's a fact. So that's written here. If one single function makes uniform integral family, then we simply say that A has AC. And now it's basically if you have uniform AC property, and weak type of limit, then the limit is going also to have AC properties. So it's preserved by weak limits. Okay. So that's another theorem. Now, is it possible to, now we have that this limit remains in the space of weakly integrable functions and satisfies AC condition. Now, can we interchange limit and integral? And the answer is yes, under mild additional conditions on x and or y. We don't have if and only if, right? We have this. Now, in this Vitali convergence theorem, it's also known. It's not just as standard as in the case of monotone convergence theorem or dominated convergence theorem, but it's one of the results from the measure theory. So, not to get into much details, actually, if you have separability, then you can get that. In the case of separability, yes. Now, if you drop separability and assume reflexivity of y, then you get convergence in the weak operator topology. So you have some additional conditions, and now there is a converse. If you assume that each of the members of a sequence satisfies AC condition and that this limit exists in a norm for any measurable E subset of omega, then the sequence is weakly uniformly integrable. That's a converse to the Vitali convergence theorem. All right, then I'm just briefly say that you can get such limits, interchange of integral and limit. Look at this. Naturally, A and T converges to AT and B and T converges to BT in certain sense, provided these are weakly uniformly integrable. Now there is this sequence of papers. What I presented so far is published this year. This is Arsenovic and Krstić. And then there is a number of papers on integration on operator valued. You see, this is the other, my colleague, who is also co-mentor of Krstić. And he also used these weak intervals of operator valued functions, so somehow it started like this. And some other results with integration of operator valued functions. And so let's skip this and move to measures because time is running out. So I'll skip this. Basically, you have norm on the space of complex measures. This is going to skip. I talked about Bochner, Danforth, and Pettis integrable, right? Integrals. What is important now when we want to integrate functions with value, it takes values in the space of complex or real valued measures, you don't have description of the dual of that space. So what you can do, you can be less ambitious and consider only special bounded linear functionals. You evaluate complex measure at a fixed measurable subset of omega. And that gives you a bounded linear function. And now you get these definitions. I talked about this earlier. The point is that you require that this function, now, lambda subscript b, lambda x of b, is integrable with respect to x. This is part C, which is the most important. And then when you consider such functions, lambda x is a complex measure defined on a space y with sigma algebra n, then if it's integrable for any b, then you're in this space. This is the space. Values here, right? Set, sigma algebra, and measure. Now, here again we have two norms. One comes from sigma algebra on X. You integrate this, get a complex measure, countably additive, that's non-trivial. It's trivial that it's finitely additive. It's non-trivial that it's countably additive. And then take supremum over all subsets of X. On the other hand, for each B, you have that integrable function of variable X and take supremum of L1 norms of these functions. Again, these are norms, these are equivalent, and these facts are not quite trivial. This space, if X is discrete, if you have a discrete measure, this space is Banach. Last time I presented this, we didn't know if this was Banach in all cases. The answer is no. Now, I gave advice to Zelina. When she gives a talk, it's fine to be clear to everybody 95% of this, at least to the expert. But the last 5% is not necessarily clear to the lecturer himself or herself. Right. And now this is the last 5%. This is where Professor Bogachev came in and linear processes in Brownian motions. So my student Krstic and I are now learning this theories from probability. So that's, I say, it's non-trivial, definitely. And so we cleared that, Bogachev cleared this open problem for us. I want to give a little tiny speech about cooperation in mathematics. This PhD student worked with Professor Jocic. There is a reference. And then he came to me, can you check this about what he's doing, certain proofs and so on. And checked, it's okay, but Krstic, we can do that in Banach spaces, no problem. And so we started to work and got this first paper on operators. We started to think about what else can be integrated. Well, spaces of measures. And then I went to a conference in Poland and asked Luigi D'Onofrio about, is it a good idea to evaluate at a fixed measurable subset and consider these as a function of X? That happens in probability theory, and that happens in variational problems, and so full of energy and optimism. Went back, and then we worked on this. And then we stuck at certain hard problems, and Krstic, this younger generation, uses all these sites and so on, posted the question, and Bogachev replied. And so how this cooperation continued, and now we have another paper published in Siberian Journal of Mathematics, also this year, 2025. Thank you.
Thank you.